Okay, let's talk derivatives. First, I want to remind you of a couple things you've already seen. If you've got an object moving with a position function s of t, so at time t it's at position s, we can find its average velocity. Change in position over change in time. And it looks like that. We also talked about how to find its instantaneous velocity at one particular moment in time. And now that we have the language of limits, we realize that what we were doing is taking a limit. So the instantaneous velocity is actually the limit of the average velocity as that time interval shrinks. So t heads towards a. That's a velocity. It's got units, and the units are whatever the units of position are over the units of time. Meters per second, miles per hour, inches per millennium, whatever. Okay? Something else we talked about was how to find the slope of a graph. The average slope of a graph is the change in y over the change in x, or the rise over the run. It looks like that. And the instantaneous slope is just the limit of that quotient as x approaches a. At the point x equals a, this is the instantaneous slope. And hey, we can write down its units too, although it's less exciting. The units of slope are the units of rise over the units of run, and usually that's inches, or meters, or whatever. So that cancels out and you just get no units. You don't say the slope is 4 inches per inches, usually. You say the slope is 4. Okay, but look, these two things look exactly the same, except for some of the variable names and function names, but we're doing the same thing. We're taking some quotient over an interval, change in something over change in something, and then we take the limit as that interval shrinks, and that gives us an instantaneous thing. So these are two cases of the same idea. The general concept is the derivative. Dun, da, da, da. Okay, so let's write it down in general. The derivative of f at a, which we write f prime of a, is this limit. X approaches a, f of x minus f of a over x minus a. That's the change in f over the change in x. And the words for this thing, other than the word derivative, is the instantaneous rate of change of f with respect to x at a. That's a lot of words. Okay, so the rate of change of f, that's what's changing, with respect to x, that's the sort of independent variable changing. That's your time, or so on. At a tells you at what point we're looking at this rate of change. Rate of change sometimes takes a long time to write, so I'll write ROC. Okay. And just like anything else, you can write down the units of this derivative. The units of the instantaneous rate of change are whatever the units of f are over whatever the units of x are. Oh, I wrote units of a, but you know what I mean. Okay. Let's look at a quick example. Let's find the derivative, g prime of 3, for this function, g of x equals 2x plus 7. If g of x is 2x plus 7, that means g of a is 2a plus 7, g of 3 is 2 times 3 plus 7, that's 13. And g prime of 3 is this limit. It's not a very difficult limit. And we get the limit as 2, right? So I just filled in g of x minus g of 3 over x minus 3, simplified, and took the limit as x approached 3. And I got 2. What does that tell me? G prime of 3 equals 2. What's another way to say that? The instantaneous rate of change of g with respect to x at x equals 3 is 2. Okay? Sometimes we don't use the word instantaneous if it's clear that we're talking about derivatives, not average rates of change. And another way to say that is the slope of this graph at the point 3, 13 is 2. Okay, that's not that surprising because what is this graph? It's a line with slope 2. But anyway, we found it using derivatives. It will be helpful to have a different way to write the derivative instead of the limit as x approaches a, etc., etc. We want a slightly different way. So here's our picture. F prime of a is this limit. Same thing I wrote on previous pages, and here's a picture showing you what's going on. X is approaching a, And there's f of x and f of a, the y values. And so this is change in y over change in x. If I call the distance between a and x h, right, so that's a horizontal distance, then another way to write x is a plus h. I start at a and I move h along and I get to x, a plus h. So I can replace all my x's with a plus h's. And what I'll get is the limit of f of a plus h minus f of a over h. That's a plus h minus a. Okay, but what goes there? What should I put instead of x approaches a? Well, I could put a plus h approaches a, but that seems a little weird. As x approaches a, that is, a plus h approaches a, that means h is getting closer to 0. So instead of x approaches a, in that limit spot, I'll write h approaches 0. These are two different ways of writing the same number, f prime of a, and sometimes one of them is easier and sometimes the other one is easier. Okay. Video question. Here's a pretty little graph. I would like to know these things. Is f of 4 positive or negative, and what about f prime of 4? Is f of 1 positive or negative, and what about f prime of 1? Remember that f prime of a on a graph tells you the slope of the graph. In general, it's the rate of change of the function with respect to x, but on a graph that just gives you slope. So bring that to class, and I'll see you there.